Okay, can you see my screen?
Yes, sir.
Uh-huh. So the first thing is really to motivate the problem. This is the stuff that we are covering is the beginning of mass transfer, which is chapter 10 of the RAND, and I can't remember which chapter. I think in the case of Willardson, it's kind of mixed all over the place. It's scattered here and there, but I don't have the chapter number handy with me right now. So the first point to be made is that you know um, mass transfer is a big topic in chemical engineering, and you've probably done an entire course on it. But in um, in and all those topics are important in biochemical engineering as well. But almost uh, all the stuff that we will cover will be on the topic of uh, mass transfer. This is mass transfer from uh, gas phase to liquid phase, or vice versa. So actually, um, the main problem that we will be looking at, and later on I'll tell you that there are other mass transfer problems, but we won't be covering them. But it's sort of the theory we do applies to those too. So I mean, the main problem that we are dealing with is if this is your bioreactor and this is your sparger and this is releasing um, bubbles that are scattered all over the reactor. But additionally, you have um, cells also, and the cells are actually much smaller. So this is not the scale, but anyway, you have cells too. And essentially, what is happening is um, oxygen is moving from these bubbles through the liquid in between to the cells. So this is the arrow that I have drawn, and I'll enlarge this to show you in a minute. So if this is your bubble, I'm just blowing it up. If this is the air bubble, and this is your cell, um, what is really happening here is in this process is that oxygen moves from the interior of the bubble across the interface. So this is the first, call it interface 1, and this is the second, interface 2. This is basically nothing but the cell membrane. Interface 2 is basically the cell membrane. So you're moving from the gaseous phase, you're moving oxygen from the gaseous phase um, into the bulk medium, and then from the bulk medium, it travels to the cell, and then at the cell membrane, the oxygen is transferred again across the membrane, which is an interface, into the cell. That's the movement of oxygen. And likewise, the cells are releasing um, carbon dioxide, and that carbon dioxide is following exactly the opposite path. The cells release carbon dioxide. Carbon dioxide goes over to across the cell membrane into the cell medium, moves along the cell medium, across the air water interface, comes into the bubble, and then these bubbles, which are moving upward, they carry. So essentially, as the bubbles are as the bubbles live for a few minutes or seconds inside the reactor, they are depleted of oxygen and they pick up carbon dioxide. And so when they come out of the head space, so I should sort of draw the picture here. This is the top of the reactor, and this is what is called the head space. So these bubbles, which is basically air, air is entering, it gets sparged into hundreds or millions of tiny little bubbles that move up through the reactor. When they come out here, they are depleted. They're depleted in oxygen and enriched in CO2 for the reasons that I have just given. And one of the main problems is to make sure that this is I would say, not one of the main, but probably the main problem of biochemical engineering. So by main, I mean the most common problem you encounter is uh, delivery of oxygen, delivery of oxygen to the cells. Now, you might ask me, why is it the main problem? And, and then so, I mean, I can give it to you first in an intuitive way, and then we can do some numbers on that. So the intuitive reason is, if you think about cells living inside the reactor, then these cells, and so the question here is why? Why is it important? Well, cells need uh, material to grow, and if you're working with a defined medium, by defined medium I mean a minimal medium containing only salts, not assembled products like ready-made proteins or ready-made uh, amino acids, what is called a complex medium. You typically supply them with various kinds of salts. I think we did that in Egley's paper. There were a large number of compounds that are given, but if you take out that list, it's basically soluble salts. So the first thing in the case, so if you're talking about a defined medium, you have to give them a whole bunch of salts. You may have to give them certain carbon sources, uh, which may be, for instance, glucose or molasses. If this is an industrial process, they take complicated mixtures as feed. It may be hydrolysates of lignocellulose, which is the big deal for renewable energy production, renewable biofuel production. So lignocellulosic hydrolysates. This is the stuff you get after you hydrolyze um, waste crops or paper or municipal waste. Um, and maybe in some very fine heavy duty processes like recombinant proteins, you may even need to add stuff like vitamins. Now all this stuff is highly soluble. All this stuff is soluble, highly soluble. Actually, not just soluble, it is highly soluble in water. you know so the feed that you are delivering over here, the aqueous feed that you're delivering to the reactor, is quite capable of carrying this stuff with it, right? You can dissolve, 200 grams per liter of glucose, um, and you won't have a problem. Water can carry it, and it goes into the cells in this concentrated form, where the cells can, eat it up and grow. But, uh, but delivery. So this is basically delivery of nutrients. So stated differently, delivery of nutrients, delivery of nutrients is very efficient. But delivery of oxygen, but delivery of oxygen is very difficult. And the reason for that simply is that the solubility of oxygen, the solubility of O2 in water is very low. I mean, the number is, um, as a rough approximation, this is highly dependent upon the conditions. The solubility of oxygen is 8 milligrams per liter, or since the molecular weight of oxygen is 32, another easy number to remember is it is 0.25 millimoles per liter. So this number will appear so often that it is worth remembering. This is a rough approximation. If you forget everything else, you can remember that you can have approximately 10 milligrams. This is the upper limit. 10 milligrams of oxygen per liter, no more. So the difficulty now is that, you know, there is very little oxygen that you can pack into the water. Stated differently, if I come back to this picture here, then the same, this feed, this feed line, which would carry so much soluble salts and carbon source and vitamins in it, it won't do squat for you when it comes to oxygen, because it'll carry almost nothing. And that's why you are forced to deliver oxygen from the sparger. Now, once you start delivering oxygen from the sparger, this is the extra line that you have created because the aqueous line isn't carrying squat for you, right? Its capacity for carrying oxygen is so limited. Then the question becomes, okay, I have this sparger and I have these bubbles that are all over there. Uh, how do I quantify what is the rate at which these bubbles are actually transferring oxygen to the surrounding liquid medium? And that's the mass transfer that we're talking about. It is the transfer of oxygen from the bubbles to the liquid medium, which are, and this is the liquid medium in which the cells are living. uh, how do you quantify it and how do you improve it? And as I told you earlier on, simultaneously these bubbles are also picking up the carbon dioxide released by the cells. So delivering the oxygen and picking up the carbon dioxide. That's really what's going on. Uh, so this is the main problem. So the main problem is in this mass transfer topic. So in this chapter, so we're always concerned with delivery of O2 and uh, removal of CO2, yeah, by the gas bubbles. Okay. Having said that, this is not, and now I should mention that even though we are exclusively focused on this, and why? So one more reason. So as I've told you, um, because it is the delivery of oxygen that is most difficult. It should not come to you as a surprise that the maximum biomass concentrations that you can maintain in a reactor are determined by how much oxygen you can deliver. Because the rest of the stuff that they need, the salts, the carbon, the vitamins, these can be easily dissolved in the aqueous stream and passed into the reactor. But since your delivery of oxygen is limited, only so much you can do, then how much biomass you get, the biomass concentration you get in a reactor, is completely determined by how much oxygen you can give, and that number is kind of known. So the biomass concentration, I shouldn't say biomass, I should say maximum biomass concentration. Maximum biomass concentration that can be attained in a bioreactor is determined by oxygen delivery rate. My iPad has stopped responding. So this is oxygen delivery rate. So in large scale reactors, I might as well give this number. In in large scale reactors, I'll give this in more detail. In large scale reactors, you cannot deliver more than, this is the upper limit of how much oxygen you can deliver. It's 300 millimoles per liter per hour. And if you know how many millimoles um, are consumed per gram dry weight of cell, you can quickly estimate what is the upper limit of the biomass concentration that you can maintain. And we'll do problems of this sort later on. So, is that background sort of clear? Any questions on this? Just this is just a background. Any questions on what I've said so far?
So it's clear.
Okay. So now, before I move on to a numerical problem, actually giving you a feel for some numbers, I should mention that even though this is the only problem that we will deal with throughout this chapter, there are other uh, uh, mass transfer problems. So, uh, this is a remark. This is just a digression from the main topic. So, there are other mass transfer problems, mass transfer problems. By other, I mean, let's just say there are mass transfer problems other than uh, gas liquid mass transfer. So we're dealing here, like I said, with a problem mostly on uh, movement of material from the gas phase to the liquid phase. But there are also problems in which you have to move material from liquid to liquid. Such problems also arise. Um, um, I'm not terribly familiar with the area, but I'm told that, for example, um, There are problems in which um, you want to degrade fatty material. And if you want to degrade fatty material, then these oils they form big globules that don't dissolve in the water. So these in this picture, these are lipid. These are lipid globules, and in the surrounding aqueous medium, again you have cells. And now you want to move, for example, this lipid gradually dissolves as the cells attack. Basically this material dissolves a little bit into the water and is moved into the bulk where it is attacked by the cells. This is a problem in I guess uh, that they use the sun. I mean, when you study this group of enzymes called lipases, the ones that degrade fats, this appears to be an important problem. And of course, you can also have the problem which you may have studied in chemical engineering, and perhaps depending upon who's taught you the course, even in um, enzyme engineering, and that is movement of material between the solid and the liquid phase. And here the the solid part. So in the case of solid liquid, these are immobilized enzymes. So basically, these are enzymes that have been um, attached to the surface or maybe even embedded inside the pores of porous particles. And the liquid medium which carries the nutrients then goes inside and carries out the reaction. This is a case in which you have to move material from the liquid into the solid phase, and the products formed then move back. So, but we'll not be covering this. We'll only be focusing on um, gas liquid mass transfer. So now let's start by doing some numbers. So this is the first exercise. Um, this is one. This is aimed at showing you. This is actually, I believe, example 3.5 of Willardson. And the aim of this exercise is to show you that because oxygen, so here's another sort of key point that needs to be made. Because there's hardly any oxygen that is stored in the liquid, thanks to the very low solubility of oxygen in the medium, it's extremely important to keep the oxygen supply going all the time. I mean, you can imagine that if you don't have a whole lot of oxygen stored in the liquid, then if you stop the oxygen supply, it will take a very short period of time for the cells to eat up all the oxygen that is stored in the liquid medium. And within seconds, as we'll see in this example, um, all the oxygen is gone. So essentially, this is an example in which you are calculating how much oxygen is stored and how much oxygen what is the rate at which oxygen is being consumed, to get a sense of how rapidly the oxygen will be depleted from the aqueous medium if you stop its supply. So um, here's the example. So this says that problem says that at D equal to 0.2, where there is a chemostat operating at D equal to 0.2 per hour, and feed concentration of glucose is 28 grams per liter. Uh, um, uh, this is the condition at which the chemostat is operating. So this is a chemostat, and it is operating at D equal to 0.2 and a feed concentration of 28 grams per liter of glucose. So this is glucose, and the organism is healthy. This example is basically production of bioethanol. Now, the first point he wants to make is, so what is the typical? So what is the typical? The main thing he wants to get you familiar with is what is the typical oxygen consumption rate here? The feel for the magnitude of the number. So, well, he first finds out, he says that, look, I'll first find out what is the volumetric rate of glucose consumption. So, this is the volumetric rate of glucose consumption, RS times X, which has units of grams of glucose consumed per liter per hour, and that we know from mass balance is simply D times SF minus S. Okay, and it turns out that at that dilution rate, this number is very, very small. So this is approximately equal to D times SF. And then he plugs in the numbers. This is 0.2 per hour multiplied by 28 grams per liter. And then he also multiplies it by 1 over 30 grams per C-mole to convert that into C-moles per hour, per liter per hour. So this gives him 0.19. So instead of doing it in grams of glucose per hour, he's converting that into C-moles of glucose per hour. So this is turning out to be 0.19 C-moles of glucose per liter per hour. This is the volumetric rate of oxygen consumption. Okay, this comes straight out of the data given to you. This is so essentially what we have said is we know the flow rate going in, right? D is just a measure of the flow rate since the volume is constant. We know the concentration that is going in, right? So we know the rate at which stuff is going in, and we also know by this assumption over here where I have put equal to 0 that everything that is going in is being almost completely consumed. So that means that the rate at which it is being consumed is essentially the rate at which it is going in, because nothing is coming out, it's eating everything up. That input data then tells us the rate at which glucose is being consumed. Okay, if you wanted to do it in grams per liter per hour, you can see it's basically 1/5 of 28. So you know right away that it's about 6 grams per liter per hour. But if you want to do it in C-moles, then you have to divide 6 by 30, and that gives you 0.2 C-moles of glucose per liter per hour. Now, why did he convert it to C-moles? He converted it to C-moles because he also knows this coefficient YSO, which we have talked about in our earlier lectures. This is moles of oxygen consumed per C-mole of glucose. So if I can maybe pause and just put down, we had this equation which is glucose, right, plus Y SO O2 plus YSN ammonia or nitrogen, whatever it is, goes to CHA OB plus blah blah blah. So this coefficient, which tells you how many moles of oxygen are consumed per C mole of glucose, is also known to him. That coefficient, which is also useful to know, he actually uses the value 0.425, but as a rough approximation, you can remember that it is about 0.5. So for each C mole you consume generally, it can be higher, it can be lower, but the order of magnitude is around 0.5. You consume 0.425 moles of O2 per C mole of glucose. Well, with these two things, you can now calculate that basically this implies that coming back, this is the quantity that we were after. We are after this quantity. We want to know how fast oxygen is consumed, typically in a reactor, and we get the number that Rs times X is on the order of 0.19 C moles of glucose per liter per hour multiplied by 0.425 moles of O2 per C mole of glucose, and that gives me the approximate number is 0.08. This is 0.08 moles of O2 per liter per hour. So this is the order of magnitude. This is just a typical operating condition. This is your oxygen requirement. If you want better to remember it in the numbers in millimoles, so this is 80 millimoles of O2 are required per liter per hour. This is your requirement. Now, to see how intense or acute the oxygen problem is, you can also now ask, you know, um, what is the storage of oxygen? How much oxygen is stored? So this is the demand for the oxygen. The next thing you write down here is what is the solubility of oxygen in water. That number, as I told you, was 0.25 millimoles per liter. So can you see the difference now? I mean, so as a rough approximation, here is the demand, and here is what is available. So, you shouldn't be surprised if this is all cleaned out in a matter of seconds. So as an estimate, so roughly speaking, all the stored oxygen, all the stored, by stored I mean the dissolved oxygen will be consumed in how many? Can anybody estimate how long it will take? It's straightforward. I'm seeking an order of magnitude here. Is there anybody? I mean, I've given you, this is the information in front of you. What is the estimated time in which it will clean out all the oxygen? Just looking for an order of magnitude. Well, it's basically the concentration of. Go ahead. Somebody was.
Sir, 10 seconds.
Ah, see this, right? So it's basically, as a rough approximation, if you want to estimate how quickly a reactant is cleaned out, you simply take the concentration on top and divide it by its rate of consumption. This gives you a quick estimate, which in this case is going to be 0.25 millimoles per liter, and you divide that by 80 millimoles per liter per hour. And if you want to see it geometrically, I am basically saying, so this is time. So roughly speaking, what I'm assuming is that this consumption rate will persist all the time. If this reaction rate persists all the time, then basically this rate multiplied, I should call this T exhaustion. By T exhaustion, I mean how much time will it take to clean out the reactant. So in reality, of course, once the reactant is significantly exhausted, the rate itself will go down. So actually, your graph, in reality, if you were to do this experiment, you would find that your concentration profile versus time, if you did such an experiment, if this is, let's say, the concentration of oxygen, it would actually go like this. I mean, it will start off linearly, but then the decline of C oxygen will go down, because once the concentration of oxygen goes down to really low levels, its consumption rate itself will decline, right? Because I mean, if it's not available, what the hell will you consume? But the calculation that we are doing is an order of magnitude calculation, saying how rapidly does it go down, means I am estimating this number. I'm extrapolating this uh, white curve, white white curve by this straight line in red color. So this is giving me right here T exhaustion. So it's giving me an estimate of how rapidly it will go down. And that number, as you can see, is basically equal to um, um, 0.25 divided by 80 comes to approximately, this is approximately 10 seconds. Is equal to approximately 1 over 300 hours, which is equal to uh, 10 seconds. So this example is intended to illustrate the importance of the oxygen supply. Yeah. And should you have any trouble visualizing this, just try to stop breathing for a few seconds and see how it works out for you. That's another way of uh, sort of seeing its importance. Okay, so is this example clear now? Now that this is just the motivational part of it. Why are we doing it? Different ways of illustrating why this is so important. So I might just add as a historical fact. I think I mentioned this earlier also. Uh, this is precisely the problem that led to the participation of engineers in biology. I mean, I shouldn't say participation of engineers. Participation of chemical engineers in biology started with this problem because in 1946 or 45, I think the biologists had already figured out how to grow uh, fungus in shake flasks and produce penicillin. But they wanted, uh, you know, penicillin to be made in large quantities. Actually, in their early experiments, the, the, they could keep somebody alive. we're talking about a single human being with all their shake flasks. They could keep a single person alive for 5 days, but then they ran out of penicillin because you just couldn't make them in shake flasks. So they quickly realized that they had to make it in large quantities. And their first attempt was to simply make large shake flasks. They were making it in 200 liter, 200 milliliter shake flasks or 500 milliliter shake flasks. They just made them bigger. And from the previous chapter, you know why this would be a problem because um, the oxygen is delivered from the liquid air, the water air interface, which scales as the square of the size, whereas the oxygen consumption scales as the cube of the size. And so it's not surprising that basically the cells were starved of oxygen. So, I mean, at that point, they invited some engineers to come and figure out why it was not happening. And that's where they started, right? So the engineers came and told them that you just have to find some other way of delivering oxygen. You just can't change the scale and get away with it. You just need to have some new ways of oxygen delivery, which are providing oxygen throughout the volume instead of only from the surface. Because as scale increases, the surface becomes more and more inadequate. And that therein lies the birth of the subject called biochemical engineering. I think by the early 50s, all these biochemical engineering journals and people popped up. And of course, now it's much more than just penicillin. Now it's, all kinds of more fancy cells. But this is the reason why the problem is important. So now, if that part is clear, then I want to move on to why, how do we, I mean, now that we've sort of understood that it is important to quantify uh, the delivery, I mean, it's clearly there's a need to figure out just how rapidly are you delivering the oxygen. You have, bubbles all over the place. How rapidly is the oxygen being delivered? Now, this stuff also, I suspect you must have done it in some form in mass transfer, but we'll probably do it in much more detail. So, let me begin by asking is the idea of mass transfer coefficient and the various theories for estimating it known to you?
I don't think so, sir.
Huh? That's surprising to me. Yeah? Once again, let me ask. Did you take the mass transfer course in chemical engineering?
So we are doing it right now.
Oh, you're doing it right now?
Yes, sir. Yes, sir.
Oh, so is it being taught by Bhaskarvar?
Yes, sir. Yes, sir. It is taught by it is being taught by Professor Bhaskar.
Oh, that's another waste of time. Okay, all right. It looks like the number of worthless guys is like unlimited over here. Okay. Uh, so let's start from the basics then. Uh, so, so you have not been introduced to the idea of a mass transfer coefficient. Is that what you're saying? Uh,
Yes,
what?
sir. Yes, sir.
Uh-huh. All right. So
We know some of
let's
the
start.
theories like penetration theory and
He has done that penetration theory.
yes, sir.
So then that seems like he's done it, right? I mean, what about film theory?
Sir, it was also in the course, but it is currently being taught.
Oh, so you're doing it, right? Uh, so let me know if I'm doing too much. Yeah, if I'm if you're already familiar, please stop me. All right. Let me start and see uh, if it's massively overlapping. with what I'm doing, then ask me to stop. Um, okay. So what we need is really, so it's one thing is pretty clear. Uh, what we need is a model, right, for uh, interface interface transfer of, in our case, gas. And actually I shouldn't say gas, because that's the name of the phase. I should say, and we'll work, we won't be talking much about carbon dioxide except at the end. Let's just focus on oxygen. Now, what do I mean by, let's first revisit the picture we have. I'm going to blow it up, and then take it from there. So, what we have, the picture we have is, if I can blow it up, this, let's say, right, is, let's say, the bubble. Mm, this is the bubble. I'm blowing it up and showing you bubble which contains air, containing air. And this, let's say, at the other end is, let's say, a cell. And as I told you, the oxygen is moving from the bubble to the cell where it is being consumed. So now, the one model of what is going on is basically the following: that inside the bubble, there is a thin film of air. So this thing over here is a film, thin film of air that is essentially stationary with respect to the bubble. So, there is no relative motion between this thin film and the bubble. It is literally moving with the bubble. This is like in fluid mechanics, what you call the no slip boundary condition, right? You assume that right next to a solid surface, even though away from the surface, a gas or a liquid may be moving, at the point where it is literally in contact with the surface, uh, there is no relative motion between the two fluids. So in this case, we are extending that a little bit by saying that it's not just at the particular interface, but in a thin region around the interface, that the film is not moving at all. So it's basically, think of it stationary, no bulk movement. It's just traveling with it. Now, this is known to be more or less consistent with physics as we know it. We know that when two fluids, uh, like a liquid and a gas, are in contact with each other, there is no relative motion at the interface. We know that to be true, and that's why we apply what is called the no slip boundary condition, right? We say that there is no slip between the two phases, they are moving together. In the same fashion, we assume that there is a film, thin film of liquid. Now, this is the medium that is surrounding. So that's the bubble. This is the cell, and in the medium, in the middle, we have the liquid medium, the aqueous medium, which is carrying the cells. And in this aqueous medium also, there is a should say. So this I will call, technical word they use is quiescent. Quiescent means not moving. And likewise, you have outside the bubble a quiescent film of medium. By medium, I mean the water that is containing all the nutrients and all that stuff. And actually, similarly, the cell is, of course, also moving around in the reactor, and that is also surrounded by an external film and an internal film. These are quiescent films that have no relative motion relative to the cell. So um, you're basically moving from uh, the first thing you have is you have stuff moving like this. This is, let's say, call it one, and then this is, so what is one? One is transfer across the phase, right? So the bubble is one phase, the medium is another phase, and the cell is a third phase. These are three different phases, right? They have different compositions. Um, Inside the bubble, you have gas. Inside the medium, you have water plus salts. And then inside the cell, you have an entirely different composition, sort of proteins and ribosomes. So these are considered three different independent phases. Since you people don't do thermodynamics, the name might be a little alien to you, but think of it as three independent um, environments with different compositions. Now you're going to move the oxygen. The first one will be the transfer from the bubble phase to the medium phase. The second one will be the movement across the same phase, which is the medium from here to here. And the third one will be the movement across now the cellular phase into the cellular phase. That is the third one. And I mean, why am I going through this? I'm going through this because actually, in principle, the problem is quite tough, right? But actually, because of some order of magnitude calculations, become very simple. It will turn out that only this matters. Only phase one matters. Nothing else matters. And only this transfer matters. So let's actually note it down. You have number one is interphase O2 transfer from bubble interior to bulk phase, and I'll define this term in a minute, to bulk phase of medium. So the word bulk here means this part of the medium, not the part that is in the neighborhood of the cell or the bubble, but the part in the medium, the bulk of the medium, the main part of it, right? That's the technical term. So so the medium near uh, the bubble will be referred to as the film or the boundary phase, and the bulk will refer to the main part. Now you need to move, as I pointed out. One refers to movement of oxygen from the bulk, from the bulk of the bubble or the bubble interior to the bulk of the medium, and the second one is transfer of O2 from um, one from bubble cell within the bulk of the medium. Okay, and finally, the transfer. So again, I should say that the third one would also be interphase. So the second one is within the same phase, and the third one is again a new phase. So the third one is again a new phase, a new interphase transfer. So it will be I think interphase O2 transfer from bulk of medium to cell interior. All right. Now, for two reasons, for the reasons I'll give now, two can be ignored. This can be ignored. Here. This one can be ignored for the following reason. Uh, Maybe I should now say actually. So stuff can be moved as we have discussed in the last lecture by both diffusion and convection. Okay. The manner in which we have formulated the problem, you can see that within these thin films, so in the film area, in this area, quiescent film, mass transfer, these by definition, because there is no movement here, mass transfer only by diffusion, because there is no movement. It's a quiescent film. It's just, the two are moving literally like a rigid body. And the same thing over here. Wherever there is a quiescent film, there is mass transfer only by diffusion. There is no convection. But in this region, this is the aqueous medium that is being thrashed around by the impellers. Most of the movement and mass transfer is by convection, and because of turbulence, this is extremely efficient. It is very, very rapid. You're throwing little pieces of water back and forth. Because this is very efficiently thrashing things about, matter is being transferred very efficiently. So that is why we neglect this. This is so fast that it is not limiting the rate at which oxygen is moving. So this negligible, we're going to neglect it. This is negligible because of turbulence. Now, this is also negligible. Can anybody guess why? So this is the mass transfer from the bulk to the cell is also negligible. Now let me give you a sense of the size. That's important to the answer. The cells are on the order of 1 micrometer for bacteria, 10 micrometers for yeasts, 100 micrometers for plant cells, whereas bubbles are on the order of at least millimeters. So the cell, so as long as we're not talking about agglomerated cells, these are just individual cells. They are at least 10, if not 1,000 times smaller than um, the bubbles. In view of that fact, I claim that the third one can also be uh, ignored. Can anybody see why?
Yes, sir. The size is negligible, so the mass transfer effects as compared to the mass transfer effects for interior of bubble to bulk would also be negligible. What you said about the order of magnitude calculation.
So, but why is size so critical to mass transfer? I mean, your argument is correct, but you basically said that since size is small, the mass transfer is better, right? Did I did I miss you or?
Yes, sir. I think so.
Uh-huh. I mean, it's the same argument, right? It's the surface area to volume ratio, right?
Yes, sir. Yeah.
I mean, so if the cell is really small, then it has a huge surface area compared to its volume. Well, the oxygen is being consumed inside the volume of the cell, but it has a bigger and so if you have a 1 micrometer cell, it has a large amount of area to pick up oxygen, but a dinky little volume to consume it. So that's why oxygen will come along very easily if you're small in size. Is that part clear?
Yes, sir.
Okay. So so basically, you have now neglected uh, the third one as well, negligible. This is since cell is small. So now you're basically left with only one major resistance. We have removed both 2 and 3 and we are left with 1. So the problem of gas transfer reduces to merely the transfer of oxygen from inside the bubble to the aqueous medium. We just don't worry about the subsequent steps. So now, essentially, the moral of this entire discussion that we have not done. By the way, this thing, point 3, this is actually discussed in transport phenomena. You describe something called, I believe, the Nusselt number or something like that, and you say that it is equal to 2. I mean, that is intimately connected to the argument that I just made. But coming back to the point, the main point here of today's lecture is that problem of oxygen delivery typically reduces typically reduces to the problem of interface. Basically, I should just say problem. It basically reduces to problem 1, which is interphase oxygen transfer from bubble interior to bulk phase of the medium. So, in other words, all we need is a theory for moving gas across an interface. That's all we need. And this theory, so this is all we need. Now, there are two theories that are prevalent, and I'll tell you this intuitively in a minute. Because, then we'll. One is film theory, and the other is penetration theory. So, the film theory, I think, is the one that I have. Actually, both theories assume that um, there is a film, but the film theory assumes that the film is not moving at all, whereas the penetration theory makes the more realistic assumption that in fact the liquid is kind of streaming. It's kind of streaming like this. The liquid is kind of, there is a thin layer. It's not a stationary film. It's actually uh, very very thin layer in which there is a kind of a gradient, velocity gradient, with the stuff moving along. And as it moves along the bubble, it picks up oxygen. And then when it detaches from the bubble, it takes that oxygen with it and moves into the bulk phase. So these are the two theories. And as you would expect, the latter theory is more accurate than the first theory. Okay, so that's the background. And now, going forward, we will actually do the mathematics. So is that part clear? Um, yeah. Yes or no?
Yes.
Uh-huh. So I didn't get even a single name. I take it that nobody's available.
No,
For
sir. I sent you the name. Yes, sir, right now.
uh-huh. Okay. All right.
And sir,
So let me just.
yes, sir, I've included Yatik, but Yatik is actually so like he has some internet issues at his place at the moment. And sir, I
Sorry.
was
Can you speak a little clearer? I
yes,
cannot follow you.
sir. I have added Yatik in the list, but Yatik has some internet issues, so I'll ask him if he can attend. Yeah.
Has what issues? Medical issues? I can't hear.
Internet issues. Internet issues. He's out.
Internet issues. Okay.
Yes.
All right.
And sir, I have added Manik because you said that he could join in the next batch instead of
Actually,
50.
I have a really simple question. How many people do I have? I don't want to do it in batches of 5, 6, right? Because I just want
Nine,
to have
nine,
huh?
nine or ten,
None.
9 or 10. Yeah.
Okay. Because
Nine.
I want to finish everything and be done with it. There are too many of them that have delayed it for far too long. I just want to
Yes.
finish it off.
Yes.
Okay. And the ones who were ill, I will do separately. The people who wrote to me that they were ill, those people I will take care of separately.
Yes.
So, but all the people in the last batch, I want to finish. Okay.
Yes.
Okay. Thank you. So I'll see you, I guess, next week on. Is Tuesday? Sorry. Monday. Is Monday a holiday or a working day?
So Monday is a holiday next week. Yeah.
Uh-huh.
So
So I
Thursday.
guess Thursday. Okay. Thank you.
Thanks.
Thank you, sir.
Thank you, sir.